Okay, we'll start. So I wanted to bring your attention to this talk, which is going to be tomorrow, here in fact, 3:30 tomorrow. Kevin Leighton Brown, who's one of our professors, will be talking about games, markets, and algorithms, reasoning about an interconnected world. So it's all about game theory, and we'll do a little bit of game theory, in the last lecture or two of this course, but there's a lot more in 422. And this was something that was developed sort of in the middle of the Second World War. Von Neumann and Morgenstern. Same von Neumann who invented computer science along with Alan Turing. Wrote a book called Games and the Theory of Economic Behavior, I think. That's where game theory started. And A Beautiful Mind, John Nash, Nash Equilibrium, was all about game theory. And in fact, Kevin talks about Nash equilibria. And the first topic that he's going to talk about, he has 4 different topics. This is all listed on the home page of the department, so you can see it there. But I think it'll be a really good talk. And it's relevant to the course, so I encourage you to come if you can tomorrow. 3:30 here, and there will be cookies and coffee and tea. There you go. Free. Can't beat that. Okay, so we're talking about uncertainty, which is something you need for game theory. So we're going to briefly review Bayes nets. We're going to talk about some special kinds of Bayes nets, Markov chains and hidden Markov models, which are very important. The Google self-driving car would not work without the use of hidden Markov models. And then we'll talk about, those are very special purpose Bayes nets. They're very, very useful for a whole bunch of applications. But then we'll talk about general Bayes nets. And in particular, the next thing we want to do, we've talked about representation. We've shown how this is a really compact, tight representation. If you've got a causal theory of how the world works, you don't need the full JPD written out. You do have it, but you have it in a very compact form. But the question is, how do you reason with that when you're given various observations? You want to see, again, the problem is you're given this theory of the world, which is what a Bayes net is. It's a theory of this probabilistic world. But you want to apply it in a particular situation. You see a bunch of things. You observe various things in the world. You want to see how that'll change your beliefs in general. Okay, so you could observe on any node and you could query on any other node. What's a good algorithm for doing that? And that's what we call the variable elimination algorithm, which we'll get to probably next time. Because we have to talk about something called factors. And factors are really kind of abstract, but they're basically just a way to represent probabilities. Conditional probabilities, joint probabilities, you name it. But they don't always add up to 1. So we just generalize the notion of probability and call them factors. And then we introduce these arbitrary operations on factors, which looks a bit unmotivated when I go through it. And it's hard to motivate it properly until you actually see how useful they are, which you will see in your assignment 4, and you will see in the next lecture. But in the meantime, you sort of have to bear with me and believe me that these are useful. And again, it's covered in detail in the text. And I do think you might have trouble with this at first, so I really urge you to read these sections of the book, because it's done in great more detail there. Okay, so we'll do a quick recap. As I say, sometimes you call them Bayesian networks, sometimes they're Bayes networks, sometimes they're Bayes nets, sometimes they're called causal networks, sometimes they're called belief networks. They're all the same thing. And then we're going to talk about these Markov chains, hidden Markov models, and then if we have time, we'll talk about general inference in Bayes nets and factors and variable elimination. I think that'll probably come on Friday. So once again, conditional independence, which is an absolutely key concept. So basically the idea is that you're interested in the conditional probability of some variable x conditioned on 2 other variables y and z. And if you learn that y makes no difference, doesn't tell you anything, then you just drop it. Okay? And we just write that as x is conditionally independent of y given z. And you can either write the probabilities in that form or in what you call the distribution form here, where you're just given the values in a table. So here's the Bayes net definition. It's a formal definition, which you should be totally familiar with. It's a DAG, a directed acyclic graph with vertices and edges. The nodes or vertices are labeled with the random variables, and each random variable has a domain, just like in CSPs. It's not just a graph, it's not called a Bayes graph, it's called a Bayes network because you've attached additional information to the graph in the form of the domains for each variable and also the conditional probability tables showing how each variable depends on its parents. Okay, so that's the additional information beyond just having this graph information. So you've got a conditional probability distribution, or sometimes we call it a table, because it's usually for discrete Bayes nets, it's in tabular form. So it's a conditional probability table or distribution, CPT, for each variable. What that does is specify the distribution of x given values for its parents. Okay? So parents x is the set of variables x prime with the edge x prime to x in the set of edges. So these are directed edges, so it goes from x prime, which is one of the parents, to the variable x, which is the one we're looking at. So we've got all its parents, they're shown as edges coming in, they're always shown as edges going down. If it has no predecessors, the parents is the empty set. And from the chain rule, which we proved, namely that the joint probability distribution for any order of x1 through xn, but in particular I'm taking this order, x1, x2, and so on. It's the product of p of x1 times the probability of p of x1, x2 given x1 times the probability of x3 given x1 and x2, and so on. The extended chain rule. And the semantics of Bayes nets is that a variable is conditionally independent of its non-descendants. Okay, this is absolutely critical. A variable will still depend on its descendants given its parents. Okay, because if I tell you some value of a variable, the guys below it are going to be affected, obviously. If you know something about this one, anyone directly below it will be affected. So you have to remember that a variable is conditionally independent of its non-descendants. So that includes its ancestors and maybe anyone off here in other parts of the graph, okay, which aren't directly related to it, but maybe have common ancestors. But nobody below that is involved here. So a variable is conditionally independent of its non-descendants given its parents. We write that this way. xi is conditionally independent of the variables, all the previous variables higher in the graph, except the parents. That's set difference, take them out, given the parents. Okay? So in other words, if that's true, then in this chain rule product, you can rewrite some of the components just dropping any of the ancestors that are not in the set of parents. Okay? All you need for any particular node is to specify it's conditionally dependent on its parents. Okay? And once you've done that, you've got the joint probability distribution as a Bayes net. You've got a total order. For each variable xi, find the smallest set of parents, which is a subset of the previous nodes, such that xi is conditionally independent of all the previous nodes, take away the parents, given the parents. Okay, once you've done that, for each variable you have to construct its conditional probability table. Okay, this is how to build a Bayes net. That is the probability of xi given the parents. And this is tricky. You have to specify a conditional probability distribution, one conditional probability distribution, p of xi, given that the parents of xi have some values, some particular set of values, for each instantiation. Okay, so you set the parents to some particular instantiation, and then you look at the conditional probability distribution of xi, of it over its values, given that set of values up the top. Okay, and if you had a different set of values up there, you'd have a different conditional probability distribution. Okay? We'll do an example of this, but for now, to test that concept, you've got your cards. Suppose a variable has 3 parents each. Okay? So there are 3 nodes coming into a variable. Each of the parents has a domain with 4 values. How many instantiations of its parents are there? This is important to know because if I don't know that, I don't know how many conditional probability distributions I need. I need one for each instantiation. Okay? Talk to your neighbor if you don't get it. So we've been dealing with binary or Boolean variables up to this point mostly, but here we've got a variable that has 4 possible values, 3 of them. Okay, and for each instantiation, look at this up here, for each instantiation of its parents, you need a conditional probability distribution. Okay, so how many instantiations of the parents are there? Try again. See what you got. Okay, a few of you are getting it. Say if you see something like this, domain has 4 values, there are 3 parents, maybe it's 4 cubed. Well, of course, there are 4 instantiations for the first variable, another 4 for the second, so there are 16 pairwise, right? And then 16 times 4, 64, for all possible instantiations of the parents. For each of those 64 values, we need one probability distribution defined over the values of x. So we can count the total number of conditional probability tables we need. We need one for each of those instantiations of the parents, so that's the 4 cubed. And we need one for we need one conditional probability table for each one of those. And there are domain number, whatever the size of the domain of xi is, that many values for the domain. So you might think it would be domain of xi times 4 cubed, but the last one you don't need, okay? So that's the total number for the x's conditional probability tables. So let's do a little example to get this right, because building Bayes nets is important. Okay, so suppose I have it's the simplest possible Bayes net. I've got 2 variables, they're Boolean, true or false, and they are disease and symptom. So this might be, I don't know, chickenpox is the disease and the symptom is spots. So we know from our knowledge of medicine that the disease causes the symptoms, not the other way around. The disease comes first, then the symptoms. Remember I said use the temporal order if nothing else? If you know the causation, use that. So disease causes symptom. But you don't always get spots. You certainly don't get them right away when you get chickenpox. And some other things cause spots, right? So there's not a one-to-one between chickenpox and spots. So we're going to build a Bayes net to help the doctor do diagnosis. So we write down the joint probability distribution of disease and symptom. Take disease first, that's x1, and symptom is x2. So it's the probability of disease times the probability of symptom given disease. That's the first thing you do in writing the Bayes net is to rewrite the chain rule. I might want to drop some guys in here if there are other ancestors that it doesn't depend on, higher up from disease for symptom, but there aren't. There's just one parent. So are disease and symptom marginally independent or unconditionally independent? Question. And I've given you some statistics down here. You know, a large number of people coming into the office, the doctor's office, we see that the ones who have both the disease and the symptoms, that's 0.0099. The disease with no symptoms, that's very rare, 0.0001. No disease and the symptoms at 0.090 because there may be other things that cause those symptoms. And most of the patients who come into the office have neither the disease nor the symptoms. So these look like reasonable statistics, right? So how do I answer this question? Are disease and symptom marginally independent? How do you know if 2 variables are marginally independent? Conditioned on nothing, unconditionally independent. Well, remember that what that means is they're totally independent events, like unrelated to each other. And in that case, if you've got 2 independent events, the probability of their joint occurrence is the product of their individual probabilities, right? So if they were marginally independent, the joint probability will be equal to the product of the marginals. Okay, so we can test that hypothesis. I'm trying to get you to answer this question, and you might say, well, of course, chickenpox causes spots. We know that, but I mean, suppose this were some data you weren't that familiar with. You'd have to test this hypothesis. This is how you test a hypothesis. The two variables are marginally independent. You get their marginal distributions. You've got the joint. You get their marginals. And then you just see, is the joint equal to the product of the marginals? If it is, then they're marginally independent. If it isn't, they're not. That's the connection. So how do we get if we're given a joint, how do we get the marginals? I'm just interested in, for any person who wanders into my doctor's office, what's the probability they have chickenpox? Independent of spots, whether or not they have spots, okay? Then I take the two cases where they have chickenpox and they have spots, and where they have chickenpox and don't have spots. And I add them up. Those are the two numbers there. I add them up, I get 0.01, right? So that's the probability of disease. That's the marginal for that. And of course, the probability they don't have disease has to be 1 minus that, 0.99. Similarly for symptoms, I just look at all the patients who have spots, regardless of what disease they have, right? So I add up the two cases where they do have spots. That's this one and this one, regardless of the disease. So for all values of the disease, I just add up where the symptom is true, and those two numbers added together give me this number, 0.1089. And the probability they don't is 1 minus that. So now I could test. Let's look at disease is true and symptom is true, compared to the product of this number and this number. So that's, I just shift the decimal point 2 places over, 0.000189, compared to 0.0099. They're not equal. Bingo. The answer is yes. Sorry, no. I had the question the wrong way around. So are they marginally independent? Conditional on nothing? No, they're not, because if they were, that would mean the joint is the product of marginals, which is not true. We just tested that hypothesis. It's false. So you have to put an edge from the parent disease to the child symptom, because the symptom is conditionally dependent on the disease. Okay, and we're going to do it that way around because the disease comes first. I just drew it horizontally to save space. Okay, so now we've got the network, now we need the CPTs. How many CPTs do we need, and which ones do we need? I put conditional in parentheses there, which is a big clue. How many CPTs do we need, and which ones do we need? Get your cards out and tell me which ones we need for this Bayes net. What statistics do I have to work out? Talk to your neighbor. It's really worth talking to your neighbor. I mean, you get more out of your time in this room if you spend time thinking about the problems, not just looking ahead in the notes, but actually trying to work out the answer. It'll help you. You'll figure out what you know and what you need to know. Okay, so put your answers up.
So like say given.
Okay, so lots of you have got green up, which is correct, but it's not the only one you need. Okay? This conditional is in brackets because this guy, you need the prior probability of the disease. Probability of the disease, and you need the probability of the symptoms given the disease. Because I've written, basically, that Bayes net is just that Bayes net just encodes this way of writing the conditional probability as a chain rule. Okay? So we need this and we need this. Right? So let's work them out. How do we work them out? So you need the probability of D and the probability of S given D. So in general, you need, for each variable in the network, remember, each variable, including this one, you need conditional probability tables, even if it depends on nothing, even if it has no parents, okay? So we know, we've already worked out the probability of the disease. We did that here to test if these were marginally independent, which they weren't, okay? But now we can use it again. We'll say the probability of disease is true is 0.01 there. Now you don't have to represent this one because I know that it's false, because I know that's 1 minus this one. No point in storing a redundant number. Okay? So that's easy. Trickier is to get the probability of the symptom given the disease. And I have to have the probability both for when the disease is true and when it's false. They're separate, quite separate. Okay? Again, I don't store the other half of this table, but what I'm showing here is the probability that symptom is true given the disease where the disease is true. Okay? That's the probability of the joint, probably S equals T and D equals T, which comes from here, that's 0.0099, divided by the probability of D, right? Which we got here. Right? So, in other words, just to remind you, so what we're computing there is the probability that S is T given that D is T. That's what we want, right? So remember, that's the probability of the joint divided by the probability of D, having that value, okay? Which is just another way of basically of writing this. If you look at it, I've got the joint here, that's equal to this times this, or if I take that over there, divide it, okay? This is all reviewed, you should know this. And we already have both of those numbers, right? 0.0099 divided by this plus this, which is 0.01. Okay, so that gives me 0.99 here. So there's another part to this table which I don't show again. I don't show the probability that S is false, given that disease is true, because that must be 1 minus 0.99 or 0.01. Okay? Don't need to compute that one. And similarly here, for disease is false, it's the probability that S is true and disease is false divided by the probability that disease is false, basically. Okay? Which is down here. Right, you just change disease true to disease false. Get that other part of the table. Okay, so I'm hammering this because you should be able to do this, okay? It's important. Okay, any questions about that? Really review. Okay. Suppose we were perverse and did it the other way around. Well, you could say they're always correct, just one may be less efficient than the other. So you could use symptom disease. You need distributions in that case. It's going that way. We need the prior on the symptom, which is P of S, and the probability of disease given system. Okay, I'm not going to go through the details of this one. You go through the details of that one. Offline. Same thing, though. You need the probability S is true, right, which we get from here. We've already worked that out, that green number. And going the other way, we need the joint probability of diseases true and symptoms true divided by the probability symptoms true, which is this number, and so on and so forth. Okay? Let you figure that one out. Okay, so where do these conditional probabilities come from? The way I've presented it is that I'm giving you all the joint probabilities. Now, that may be true, one way to do it. But it's not normally the starting point because there's a huge amount of data there you have to provide in order to get the more compact one. A more usual way to do it is to say, try to figure out what's the network structure first. What's the graph structure? And then I'll fit the CPTs to that graph structure. Okay? And there are two ways to do that. Either you have an expert, like a doctor, who says, well, of course, disease causes symptoms, not the other way around. So that's the right causal distribution. Or there are various machine learning algorithms which will hypothesize or guess a graph structure, and they see if that fits the data. If not, they do local search. They do a minor perturbation to the graph structure, change a few arcs, and see if it gets better. It gets to be a better fit to the data. If not, try something else. So on. So that's very much like the stochastic local search we've already done for CSPs, except now you're searching over graph structures rather than values for solving CSPs. We're not going to go into any detail on that. You have to take a grad course in machine learning from Nando. I highly recommend 540, which is a follow-on to 340. And then you fill in, once you've got the best structure, then you can fill in the conditional probability tables. And actually, of course, there'll be an iteration back and forth between finding the structure and filling in the tables. And again, you can either use an expert domain knowledge, or you can get observed data. As I said, you could look at all the patients coming into the office and see who's got diseases, who's got spots, who's got both, who's got neither, who's got one and not the other. And then fit your CPTs to that data the way I just showed you. Okay? But we're not going to dwell in any detail on that. It's the kind of thing you do in a machine learning course, or the advanced AI course, 422, will look at that as well. So we're going to get back to these specialized Bayes networks, which are really important. Markov chains are a classic mathematical structure. The idea is you've got a dynamical system, basically. So a dynamical system is something like you studied in physics or in chemistry. You have a state of the system, and you have laws of how the state evolves over time, either with continuous or discrete time. And the state description encapsulates everything you need to know about the system, right? Newton's laws say if I know the position and velocity of every particle in the universe, I can predict the entire future of the universe. I don't need to know where they were in the past. All I need to know is their current position and velocity, right? It's not past dependent. So that's a very simple example of the universe, simple example of a Markov chain. So, but we're going to assume that these aren't deterministic laws like Newton's laws of motion, but they're stochastic laws. But the future state only depends on the current state. So this represents a system. You can think of time as going this way to the right. And this is the initial state of the system. It jumps into the next state, then jumps into the next state, and so on. Okay? Because of that, if I'm interested in how this thing evolves, at any time t, in general, the state of the system at the time, this is x at time t, will depend on all the previous states up to t minus 1. But if I have this special property where the state completely encapsulates the entire history, that's all you need to know, say the position and velocity of every particle, then the probability of distribution of xt, it only depends on where you were at t minus 1. You can forget all the previous history. It's irrelevant to how you got to this state. Once you know you're in this state, I don't care how you got there. Okay? And this is true of a very large number of physical and chemical and biological systems, once you get the right description of state. So this conditional probability distribution is called the state transition probability, okay? Because you're going from one state to another. And this may be, there may be a finite number of states here, and every time step you go into you're in a particular state here, you go into a new state with some stochastic property, some randomness involved. So as it says, X conveys all the information about the history that can affect the future states. The past is independent of the future, given the present. So the present cuts you off from the past history. You don't care about it. Okay? So if I'm interested in all of these states, then I have to write down the joint probability distribution again. The JPD will be the joint of the state of x0, the state of x1, up to the state of xt, which again will be the product of all the conditionals. Start with the prior on x0 times probability of x1 given x0 times the probability of x2 given x1, and so on. But notice there's only one parent for each node, so for each node I only have to look at its previous parent, the one before it. So that's a general Markov chain, an even more specialized, see, it's a very special kind of belief network, basically. An even more special version of the Markov chain is where it's stationary. The laws of motion don't change over time. Okay? So in other words, given that you're in a certain state at a certain time, the distribution over the next state will be the same, whether it's minus 2,000 or plus 2,000 time. Completely independent of that. So in other words, if this condition is true, the probability of xt given xt minus 1 is equal to the probability of xt prime given xt prime minus 1. If that's true for all times t and all times t prime greater than 0, then it's stationary. Its properties don't change over time. And there's some really nice mathematics associated with this. You'll find that any stationary Markov chain will go into a finite limit cycle, or will be an absorbing state, and it'll get stuck in that state, so on and so forth. We're not going to do all that, but for what we're interested in, we need to go to robots, okay? So, because that's all I'm interested in. So, once it's stationary, there's just two things you have to specify for the Markov chain. It's initial distribution over the states, which is stochastic, and then for any time t, how its values depend on the instantiation of the previous state. It's a very simple model, very few numbers, often very natural, because typically the laws of physics don't change over time, right? It's what we believe. Even back in Big Bang days, it's still the same laws of physics, just different initial conditions, so on. So there's a classic example of the drunkard's walk. Maybe in one dimension that you've got a drunk walking along a sidewalk, and there's 0.9 probability they'll go to the right, and 0.1 they'll go to the left, right? What is the distribution over time of that drunkard's position? Or a robot. You might imagine like a Roomba-type robot moving in two dimensions, and every time it's moving at a certain velocity in a certain position, and the next time you look 1 second later, it'll be moving at a different position, a different velocity. But that doesn't depend on the time. Those statistics are always stationary. So that assumes that you can observe the state of the world. Now, typically you can't observe the state of the world. You can only observe properties of the state of the world. So that gets us into what we call hidden Markov models, where it's basically a Markov chain. It's a stationary Markov chain, but you get observations from the world every time step. Okay? So it may be a robot car driving down a road, and it's looking around, and it sees various landmarks from Google Street View, say, which is how it works, right? But these are noisy, and the sensors are noisy, and the position in the world is noisy, et cetera, et cetera. So you get some observations of the world which give you some information about your current state, but not the exact position. Just usually some noise envelope around your guess as to what the current position is with some variables. That's typically the kind of thing we're talking about. Okay, so at each time there's some observation, and we'll use this notation always. Any shaded node means I'm observing that node. Okay, so the Roomba may say, I'm over here, and it may be slightly lying. It may have a laser that's looking out at the world and it figures out where it is, or you're looking at the robot with a camera, and your camera has some digitization noise because it's a finite number of pixels, and et cetera, et cetera. You've got some data about the state, but you don't have the state itself, which is what you're really interested in, okay? So you have to infer the state. You do know the laws, the dynamics, how this state changes from one to the other, and you know how a state will affect the observations. You just don't know what the state is, but if it's in a certain state, you know what distribution the observations will have. They'll never be one-to-one. You'll never get perfect information. So, and these are all stationary. So you have this, what you call the state transition probability, specifying this arc here. That's the CPT of this, given that. And the observation probability, which is how this depends on that. So here, the observation will depend on the state, right? So you've got, just as in a Markov chain, you have these transition probabilities, but we also have this new model, which you could call the sensor model, because this will be some kind of sensor data you're getting. And there'll be some fairly precise probabilistic information about how the current state here will affect your observation. So there's some correlation between them. Okay, so suppose in general, what we're going to be interested in is estimating the current state, right? As we go along, we want to update the current state estimate based on the new observation. You have some old observations in state, which give you an estimate of this state. Then you're going to jump to this state. You get a new observation, so you know you have uncertain information about this state from where it came from, and you have uncertain about this state based on the observation you have. And of course, you want to combine those two sources of uncertainty and reduce the total uncertainty about your estimate of the current state. That's basically the job, right? So again, the joint probability distribution of this hidden Markov model, if we take all the state variables and all the observation variables, and we're interested in their joint, then it'll just be this is a Bayes net here, and its JPD is just as before. It's the probability of all these guys times the conditional of each node given its parents. And each of these only has one parent, and each of these only has one parent. Okay, so it's just the same rule as we had before for the JPD of a Bayes net, except it's specialized for this hidden Markov model situation. We're not going to go into much detail about these. It does in the book, and we certainly encourage you to read it. There's lots of good stuff in there about robot tracking. I just wanted to introduce it as an example of a Bayes net to show you that, this is important stuff, because this is how Google car manages to drive hundreds of thousands of kilometers without killing people yet. That'll be the next problem. So you can imagine that this robot is moving at random. So I know the statistics. The Roomba tends to go to the left 90% of the time, but it goes to the right 10% of the time. That would be this. And I know how my camera model works. Given a certain position, what am I likely to see in the image? And there's another example of this in the book, which you should look at. So filtering in HMMs. So as I say, the basic idea is that you're going to be given, you'd like to know at some time t, what is its distribution given all of the observation you have up till that time. Okay? And then I'd like to extend that. So you're given the initial distribution of states here, right? And then you get an observation here, and you've got that distribution there. So I got this actual observation. I need how to compute on a Bayes net where I've got these two unknown variables and this known variable here. How do I compute the distribution of this variable? I'm not interested in this one because I'm now up to this state. Okay? And we know how to do that. We did that with the JPD right in, I think, in Uncertainty 2 lecture. We talked about how do you take the JPD of any distribution and condition on certain evidence and then query certain variables. You know how to do that. You may forget it, that you know how to do that, but you do know how to do that. We did it. So you can do that again. And we're going to keep doing that, keep updating it. So the idea is that at any point, we will say we're at this point, which might be some arbitrary point in time. We have the conditional distribution of this, given all the previous observations, and we want to update that to incorporate a new observation in this new state. And this is basically an example of filtering. There's a very simple algorithm for updating the previous estimate to the next estimate. So you've got basically an online algorithm which, as the data keeps coming in, because this is coming in over time, you're going to be updating your estimate to the best current estimate based on all your previous observations. You've never actually observed the state. You always only have these indirect observations. But you can get surprisingly accurate state estimates once you know these transition probabilities this way and this way. Okay, and it's actually an example of dynamic programming. So, but that's, as I say, there's more on this in the book. You're not responsible for it, but I thought you might be interested. That's how modern robots work. Okay, basically, this simple theory. How they, based on uncertain information, get pretty confident estimates of where they are in space and what their velocity is, for example. Because they may have many, I just talked about one sensor, but of course, a typical robot will have lots of sensors. It will have vision, it'll have ultrasound, it'll have lasers, it'll have an inertial measurement unit, et cetera, et cetera. It'll have a GPS system, like your phone, et cetera, et cetera. And your phone also does this because, the phone, you have cell towers, which give you noisy estimates of where you are based on the cell towers you can see. And you might have a GPS sensor in there. You might have Wi-Fi sensor, which might and can use the current presence of Wi-Fi networks and their relative strengths. All of these are the kinds of things we're talking about. You want to combine all that uncertain information and get a really good location on your Google or Apple map. Right? That's what's going on in the phone. Yeah.
So for a robot, what happens when you first turn the robot on? So it seems like if this has been running for a while, you have MAs, but what happens like when you just, at time 0, you turn the robot on?
Yeah.
How is it supposed to make any kind of sense of its position at time 0? Like it has no map, if you will, like even no relative map.
Okay, so then you would have to do something like a uniform prior. So you just say, well, I know it's in this building. So it could be anywhere in the building. I just give it equal probability to every possible position in the building. And then as you get sensor readings, it'll very quickly converge to a much tighter estimate.
So generally uniform priors are used over other priors, like say a Jeffreys prior or something that would give some weight to...
Yes. Yeah, I mean, people use different versions, but uniform prior is usually the one that people use. I mean, we're talking, when you turn your cell phone on the map, you start with a very big region of uncertainty, and it slowly narrows down as it picks up more sensor data. That's basically what's going on. That's the variance of the estimate. Any other questions? Okay, so we've got all those special cases of Markov chains and hidden Markov models, which are really important. But we need more general structure, so we need to know how to do this in general, right? So, as I said, in general, you can do this you can do very efficient inference in hidden Markov models using a filtering idea that you're just updating the current estimate using the latest information. You don't have to recompute the entire network, is what I'm saying. Okay, you just incrementally add each observation as it comes in from different sensors. But for general Bayes networks, we're going to do an offline algorithm. That's as soon as we've got all the network, we've got all the data, we've got all the evidence at once, and we need to compute the posterior distribution given the network and given the evidence. Okay? It won't be as efficient, but it's much more general than the special case we just talked about. And this we are going to do in detail. Okay, so as I said, we're going to use this convention that the observed variables are shaded. And so, for example, you might be able to observe whether a student has understood the material. You quiz the student or whatever. That might be the observed variable, and you actually want to predict the exam grades and the assignment grades given the extent to which they understand the material. Or more likely, you might observe the assignment grade and try and figure out how much they understood the material. You might have both grades, you might only have one grade. Okay? Similarly, in the alarm case, this is more common where the evidence is at the bottom. Okay, so here the alarm goes off. So what we're doing here is setting that variable to true, basically. I've observed alarm equals true. And then I want to say, what is the probability if someone was smoking at the sensor given that alarm is true? I'm conditioning on the observations, okay? So, what kinds of inference can we do with this? Assuming we know how to do this inference, we don't know how to do it yet, but we will. We use variable elimination. But this is to motivate you to think, why are we going through all this algebra? So, Here's an example where we're doing diagnostic information, just as we did with the symptoms and diseases, and this is most typical, I would say, where you're given evidence at the leaves of the DAG, observations, people are leaving. Leaving is true. From that, I can't hear the alarm. I don't know if there's a fire. I'd like to say, if people are leaving, what's the probability that there's a fire? Given that the people might be leaving because of a false alarm, and they might be leaving because it's lunchtime, you know. So I need to be able to work out the probability that fire is true, given that leaving is true. And I don't care about the alarm, right? So I projected out the alarm. Okay? So we know how to do this in general. Let's say we're using inference by enumeration. We want to do it in Bayes nets more efficiently. Here's another example. Suppose I set a fire. Fire is true. What is the likelihood that people will leave given there's a fire? So this is predictive. I'm going forward. Okay? You could do it both ways. You could say there is a fire and people are leaving. Has the alarm gone off? Be an interesting question to answer. So you're using both forward and backward prediction. And the same algorithm will do all of this uniformly. And here's a really interesting case. If the alarm goes off and you know someone is smoking, what's the probability of the fire given that the alarm is true and smoking is true? This stands for tampering, but in this case it's smoking. Smoking is the form of tampering, right? If you compare that to the probability of fire, the prior on fire might be quite low. Or let's say the probability of fire given the alarm has gone off. And you don't know about tampering here. So I'm querying given probability of fire given alarm is true. That might be some number, okay? Now I say, well, I know there's someone smoking at the sensor, so that gives me a reason to believe why the alarm went off. I don't need the fire to do that. So actually the probability of fire given alarm is true and tampering is true will go down. This is called explaining away the cause. I have a cause for this symptom, so I don't need another one. Okay? This is quite common, as you can imagine in diseases, right? If I've got some explanation, if I know this person has chickenpox and they have spots, I'm less likely to believe they have measles, because I don't need another explanation for spots. One is enough. Right? So we need to do all of that kind of stuff. Condition on almost any, condition literally on any, the value of any variable in the network, and query any other one. Perhaps projecting out the ones I'm not interested in, or perhaps querying on all the remaining variables. Okay? So that's what we need to do. As I say, you already know how to do this. So we've given the Bayes net, we've given observations on a subset of the variables, so we're given values. By observations, I mean I bind certain variables to certain values in their domain. And now I give you another subset of variables that are queried that I'm interested in. So I want the conditional probability y given that e is equal to its values. And I'm not interested in the other variables that aren't in either y or e. Okay? So the how, we're going to do that by running this so-called variable elimination algorithm. But you can already do this, and you should know you know how to do this. You should be able to do it on simple examples using inference by enumeration. Okay, remember how we did it in this lecture? The Bayes net represents the JPD. You could actually just work out the JPD into a full table of all variables of all possible values. You have their joints, okay? Once you've done that, then you do inference by enumeration. That is, and how you do that, you rule out the rows in the table that correspond to the evidence being false, that it's not the case, right? And then you proceed, follow that algorithm. But it won't scale out, so that's why we need this more efficient algorithm. So we got to this point in the lecture. Now we have to worry about these ugly things called factors. And I really recommend that before Friday you read that section in the book, because it's hard to understand why they're important and hard to understand them if you haven't gone through some details first. So I really recommend that. And then look at the variable elimination algorithm. Okay? So that's it for today.